Hello my friends and welcome back to the You Can Do TV channel. A retractable roof system like the one planned for Mercedes-Benz Stadium introduces construction challenges rarely seen at this scale. Designed as the first roof of its kind, the structure demands an approach that balances raw lifting power with exact coordination across every move. Crews prepare massive truss sections on the ground, aligning connection points so each lift fits the overall geometry planned for the fixed roof area. Didn't expect roof steel to feel this intense once it leaves the ground. To move components of this scale, ironworkers rely on the largest American-made crawler crane available. The crane is positioned to manage extreme loads while maintaining stability across uneven terrain surrounding the stadium site. Each truss installation requires constant checks, controlled rigging, and careful timing between ground teams and crane operators. That lift feels like controlled force refusing to rush anything. More than 100 truss installations are scheduled to complete the fixed portion of the roof. Each placement locks into neighboring sections, slowly forming the recognizable circular pattern above the seating bowl. Wind conditions, elevation, and weight distribution all shape how each lift is executed. This is why planning matters when steel weighs more than imagination expects. Ironworkers work at height to guide connections into place, securing bolts that will permanently support the roof system. The job carries real risk, demanding focus from start to finish. As sections accumulate, the roof begins to assert itself as the defining feature of Mercedes-Benz Stadium. How calm the crew stays with that much weight overhead. Hydropower at Poço sa Tupamona is designed to turn river force into stable electricity for Sulawesi, blending long-term infrastructure with controlled heavy construction. The project by Kala Group uses civil structures and electromechanical systems supplied by PT Bukaka Teknik Utama. Water intake structures are formed first, directing flow toward the powerhouse. Turbine units are placed inside the powerhouse to handle continuous load. Generators above convert rotation into electrical output for grid stability. Transmission equipment connects the plant to regional lines. This setup feels like quiet strength doing serious work. Control systems regulate water volume, speed, and output as river conditions change. Adjustments protect equipment while keeping efficiency steady. You'd never guess how much coordination sits behind that steady flow. The plant supplies renewable power around Poço today. Feels like the river finally found a long-term purpose here. Keeping traffic moving while construction advances is the core challenge solved by the Underbridge 2.0, a mobile overpass system built to carry vehicles safely above active motorway works. Developed under commission from the Federal Roads Office Astra and implemented by Marti Technic AG, the structure allows lanes below to remain operational instead of forcing closures. Didn't expect an entire bridge to feel this practical once it's rolling into position. Large steel modules are fabricated to standardized dimensions so they can be transported and assembled quickly on site. Support frames are positioned alongside the motorway, forming a stable base before deck sections are guided into alignment. Hydraulic systems raise the structure to the required height, creating clearance for construction activity underneath. That lift looks like controlled strength refusing to waste motion. Once elevated, roadway panels are secured to form a continuous driving surface across the bridge. Barriers and access elements are added to channel vehicles smoothly over the span. The bridge is engineered to handle daily traffic loads while maintaining predictable behavior under constant use. This setup feels like infrastructure thinking ahead instead of reacting late. When construction below progresses, the Underbridge 2.0 can be shifted forward. Wheels and guidance systems allow the entire assembly to move in stages, matching the pace of roadwork. Crews reposition it without dismantling the main structure, saving time and reducing disruption. You'd never guess how much planning hides behind something that moves this calmly. By keeping traffic above and work below, the system reduces congestion and improves safety for workers and drivers alike. Feels like choosing progress without forcing anyone to stop. The Underbridge 2.0 stands as a working solution where mobility and construction share the same space. That balance alone could change how road projects are handled. How does a highway ramp disappear without stopping the city beneath it? That question sits over Chicago as the Illinois Department of Transportation prepares to remove Unit Number 2, the westbound Ontario Street ramp crossing above southbound I-9094ths. Scheduled for a tight June weekend, the operation demands strict sequencing so traffic below remains protected while the structure above is taken apart piece by piece. Closing lanes isn't an option here, so removal has to happen in motion rather than isolation. Didn't expect demolition planning to feel this deliberate. Crews isolate the work zone and reinforce protection over the Kennedy Expressway. Temporary barriers and shielding are positioned to catch debris before any cutting begins. Heavy equipment is staged nearby, timed to move in as sections are freed. Every placement on the ground directly affects what can be removed above. That setup already hints this won't be rushed. Concrete deck sections are addressed first. Saw cuts divide the ramp into manageable segments, allowing controlled removal instead of uncontrolled collapse. Each segment is lifted clear and transferred away from live lanes. Segmenting the deck keeps loads predictable during every lift. With the deck gone, attention shifts to the supporting elements. Beams and structural connections are separated in a planned order so loads never shift unexpectedly. Cranes handle each piece individually, maintaining balance as steel and concrete leave the span. Load paths are reduced step by step rather than broken all at once. You'd think gravity would argue more, but everything stays obedient here. As Unit Number 2 continues to come apart, crews monitor conditions below constantly. Any adjustment to timing or sequence happens immediately to protect traffic and workers. Debris removal runs parallel, clearing space so the next operation can proceed without delay. Keeping the roadway active limits how long each task can occupy the airspace above. This is why coordination matters when thousands of cars pass just meters away. By the end of the weekend, the Ontario Street ramp is no longer overhead. What remains is open sky above southbound I-9094ths and a cleared corridor ready for the next phase of roadway changes. Hard to believe a structure that once carried daily traffic can vanish this cleanly. The demolition shows how controlled removal can coexist with one of Chicago's busiest expressways. Feels like subtraction done with discipline instead of force. Keeping trains steady depends on what sits beneath the rails on Metro Transit St. Louis lines. Wooden rail ties are removed and replaced to support Metrolink tracks, while service reliability stays the priority. Crews mark the work zone, lift rails slightly, and pull out worn ties without shifting alignment. That careful lift keeps geometry intact under live track conditions. New treated ties slide into position, and fasteners secure the rails back down. Ballast is adjusted to restore support and load distribution before trains return. You don't think about ties until a train glides over them like nothing changed. Regular replacement cycles reduce defects and extend track life across the Metrolink system. By focusing on ties, Metro Transit St. Louis maintains stability below the rails, while riders notice fewer disruptions. That result is the point of maintenance done right. An LNG facility spanning Curtis Island supports gas processing and liquefaction for Australia Pacific LNG exports. Gas processing systems prepare feed gas for cooling, removing impurities so liquefaction can proceed under controlled conditions. Construction of the LNG facility required coordinated civil, mechanical, and systems installation across the island site. Large-scale infrastructure like this leaves no room for rushed sequencing. Liquefaction converts treated gas into LNG for efficient storage and transport. Every stage depends on alignment between engineering plans and field execution. Safety remains embedded throughout operations, guiding layout, access, and operating discipline. It's striking how much planning sits behind a steady LNG output. The facility reflects years of structured development rather than quick assembly. A timed sequence controls how Fisher's bollard fence panels are installed during demo day under strict site limits. At 10:10 a.m., the shift opens with equipment positioned inside the 60-foot Roosevelt easement, while wind speeds already push between 25 and 35 miles per hour. That weather window alone sets the tone for how tightly everything must stay on schedule. By 10:15 a.m., a loaded truck reaches the job site, followed at 10:30 a.m. by the first set of 7 18-foot panels being prepared for placement. These panels establish the initial structural rhythm of the fence line. At 10:50 a.m., wire mesh is fixed onto the lower angle iron, adding lateral stability before lifting operations begin. 10 minutes later, the first machine swings 56 feet of fence directly into the trench. Seeing that span move as one piece explains why alignment can't be treated casually. At 11:05 a.m., crews focus on fence alignment, locking position before concrete arrives. The concrete truck pulls on site at 11:10 a.m. and placement starts at 11:15 a.m. No bollard or mesh movement during this stage is non-negotiable. Once the base is secured, installation continues without hesitation. At 11:20 a.m., the second set of 18-foot fence sections drops into place, followed at 11:30 a.m. by the first 30-foot panels moving into the trench. This is where pace matters more than force. By 11:45 a.m., the final 30-foot panels are loaded, closing the main installation phase. At 12:30 p.m., a total of 192 feet of bollard fence stands completed in just 1 hour and 50 minutes. That timeline feels tight, even on paper. Throughout construction, work remains fully within U.S. boundaries, never breaching the USA-Mexico border. After 3 hours of curing, the excavator is stripped away at 3:05 p.m. 2 minutes later, it shifts position, ready to reload with another 7 panels and repeat the cycle. Efficiency here comes from sequence, not shortcuts. Balancing hundreds of tons above an active city corridor, the U-shaped beam launcher and gantry crane system used on the Jakarta LRT Metro Bridge is built to work where space leaves no room for error. Precast U-shaped beams arrive on site after factory casting and curing, already holding their final geometry. The gantry crane spans the elevated alignment, positioning itself along the piers to receive each beam. This is the kind of setup that makes you realize how planning quietly carries the real weight here. Instead of ground-based lifting, the system operates entirely above the structure, keeping roads and rail activity below largely uninterrupted. Once the crane locks onto a beam, controlled hoisting lifts it clear of transport supports. The launcher frame guides the beam forward along the bridge line, maintaining alignment while load sensors track balance across the span. Seeing that beam glide forward feels unreal when you remember what's moving underneath it. Movement speed stays deliberately restrained, allowing constant correction rather than forceful motion. At the installation zone, fine positioning takes over. The launcher lowers the beam gradually until it meets bearing pads on the pier caps. Small adjustments in lateral and longitudinal axes ensure the U-shape seats evenly, avoiding stress concentration once permanent loads arrive. Miss that alignment, and the structure will never forgive it. Once seated, temporary supports hold the beam steady while final checks confirm elevation and orientation. After placement, the gantry advances to the next span, repeating the cycle without dismantling major components. This repeatability is what keeps the project moving at scale, span after span, above dense urban infrastructure. There's something oddly calming about how routine replaces risk once the system settles into rhythm. No drama, just control. Over time, the launcher becomes less of a machine and more of a moving platform for consistency. Through this method, the Jakarta LRT bridge grows piece by piece, relying on engineered restraint rather than spectacle. You don't hear celebration when a beam lands, but you can feel the quiet relief when everything lines up exactly as planned. How can two auger machines work side by side to install a 62-meter embedded pile without losing depth control underground. The DMA double machine auger method answers that question at the Songdo site in Incheon. Preparation focuses on the HCP composite pile, assembled to its full length before any drilling takes place. This upfront setup matters once depth increases and adjustments become limited. A pile this long leaves no room for guesswork later. The first drilling rig moves in, boring the ground while inserting the lower casing to stabilize the hole. Soil removal and casing insertion progress together to prevent collapse as depth increases. The second drilling rig follows, continuing boring and installing the remaining lower casing. With two machines sharing the workload, alignment stays consistent across the full depth. Seeing two rigs trade responsibility like this feels strangely reassuring. Once target depth is reached, extraction begins in reverse order. The second rig withdraws its upper screw rod, clearing space while maintaining wall stability. Next, the first rig pulls out the lower screw rod. This staged withdrawal keeps pressure balanced inside the borehole. Pull too early or too late, and the ground would definitely have opinions. With the bore prepared, the HCP composite pile is inserted smoothly into position, guided by the casing system to maintain vertical accuracy. Casing removal follows in two steps. The second rig extracts the upper casing. Then the first rig removes the lower casing, transferring load gradually to the surrounding ground. That slow handoff is where confidence quietly replaces tension. Final penetration depth is checked against design values to confirm full bearing performance. This DMA operation reached a domestic record depth of GL 62 meters during construction of the Songdo Waste Pretreatment and Resource Circulation Facility. The method prioritizes control, sequence, and cooperation between machines rather than force. When everything lines up, the depth almost stops feeling intimidating. "12 months of construction at the Parson Street Underbridge are condensed into a time-lapse. The Parson Street Underbridge project, delivered by Network Rail with Kier, unfolds through carefully staged construction windows. Early activity focuses on site setup, traffic management, and rail protection, creating safe zones that allow crews to work beneath active lines. That quiet preparation decides whether everything later moves smoothly or not. Structural access follows, with temporary supports and platforms installed to reach key bridge elements. Demolition and removal of worn components progress in controlled sections to keep loads balanced. This is the part that feels tense even on fast forward. New structural members are then positioned, lifted into place, and fixed to restore load paths across the underbridge span. Concrete works appear next, forming deck elements and support zones that reconnect the structure as a single system. Services, drainage, and finishing tasks move in behind the main structural phases, tightening the bridge back into everyday use. Seeing layers return one by one changes how you think about just a bridge. Throughout the timeline, inspections and adjustments repeat to confirm alignment and performance before each stage closes. 12 months of coordination, restricted access, and sequencing are condensed into few minutes. How much planning disappears once the bridge looks ordinary again?
A narrow roadway beside an active railroad crossing demands a surface that grips fast and holds steady. In this section of Chip Seal Part 4, crews apply chip sealing where traffic timing, rail clearance, and surface bonding must align without hesitation. Preparation is already evident as the roadway edge is defined and cleared. The chip spreader follows the distributor truck, keeping distance tight to avoid overlap near the tracks. Binder is applied in a controlled strip, sized to accept aggregate without excess. This is the kind of setup where spacing matters more than speed. Every pass respects the crossing geometry. Aggregate drops immediately after binder placement. The spread pattern stays consistent even as the roadway narrows. Near the rails, alignment becomes stricter to prevent loose stone from reaching the steel surface. Rollers follow in sequence, pressing chips into the binder while maintaining clearance from the crossing hardware. Traffic control remains active throughout. Vehicles are released in short intervals, allowing compaction without trapping cars on the tracks. Nobody wants to be the one waiting on rails while fresh stone sets. Rolling continues until embedment reaches target depth, locking aggregate in place before movement resumes. As work progresses, adjustments are made to spray width and chip volume. The crew compensates for slope, shadow from rail structures, and slight elevation changes. It feels like threading a needle with asphalt and stone. Each adjustment keeps the seal uniform across the approach and exit zones. Final rolling tightens the surface and removes excess movement. Loose aggregate is minimized to protect tires and signaling equipment. This is where patience quietly pays off. The finished section blends seamlessly with the rest of the roadway, despite the constraints. What stands out is coordination. Chip sealing next to a railroad crossing leaves no room for shortcuts. Repetition, timing, and control guide every move, keeping the surface stable and traffic moving safely. Crosswalk markings have to survive heat, traffic, and constant turning tires. On 54th Street in San Diego, a thermoplastic crosswalk is installed using a Super Leo striping machine operated by Precision Striping, Inc. Traffic control is set first, creating a clear working window while crews stage material and tools. Thermoplastic is heated until it reaches a workable state, then fed into the Super Leo. The machine guides molten compound onto the pavement through shaped dies that define each bar. Once the material hits asphalt, timing matters more than strength. Glass beads are dropped immediately so reflectivity bonds while the surface is still hot. Miss that window and the shine never fully locks in. Each pass follows alignment marks already laid out across the roadway. Operators control speed to keep thickness even across every stripe. Those clean edges decide whether the crosswalk ages evenly or flakes early. Cooling happens naturally within minutes, allowing traffic to reopen without long delays. That quick return always feels like cheating the clock. The finished crosswalk resists wear far longer than paint under heavy use. Seeing cars roll over it moments later feels risky, yet it holds. This method keeps maintenance cycles longer and streets moving. Night crews repeat this routine across intersections citywide. The KEMR OCEK 140 chain cutter is used in canal and pipeline construction to mill precise slots directly along confined channel edges. Mounted to a carrier, the EK140 advances steadily as its cutting chain engages concrete and compacted soil. Material is removed in a controlled path, allowing operators to follow alignment without widening the trench. That narrow cut saves more space than it seems. The chain keeps contact uniform, producing consistent depth along the run. Seeing debris clear so cleanly feels reassuring. Progress continues section by section as the attachment maintains stability under load. Spoil is lifted out without collapsing nearby edges. This is where control matters more than force. Once the channel profile is complete, the path is ready for pipe placement or reinforcement. No extra cleanup sounds like a small win, but it adds up fast. The Tesmec 1475 Rock Hog drills through rock to form deep foundation shafts on U.S. construction sites. On site, the machine is positioned and stabilized, setting its stance before drilling pressure is applied. Hydraulic systems drive the rotary head downward, forcing cutting tools into rock layers that refuse to yield easily. This isn't speed work, it's controlled force doing the talking. As drilling progresses, spoil is lifted out through the auger path, keeping the bore clean and ready for depth extension. Depth control remains constant, as the rock hog maintains alignment while penetrating variable geology. That steady posture is what keeps the hole honest. Once the target depth is reached, drilling pauses to allow inspection and confirmation before the next phase. Reinforcement elements are prepared nearby, time to move in without delay. Miss that timing, and everything backs up fast. The bore is conditioned, ensuring walls remain stable for structural placement. Reinforcement cages are then lowered carefully into position, guided to maintain vertical accuracy. Concrete placement follows, filling the drilled shaft from base to surface to lock load paths into the ground. That moment always feels final, like the ground just accepted the deal. Excess material is managed, and the rig retracts cleanly, ready to relocate. Across foundation sites in the USA, the Tesmec 1475 Rock Hog shows why deep drilling demands patience, force, and consistency. No shortcuts here, just stubborn ground meeting a machine built to answer back. The Komatsu 575 Superdozer delivers controlled pushing force for heavy mining work at Stockton Mine. This machine operates in both manual and remote control modes, allowing control from outside high-risk zones. Rated at 1,200 horsepower, it can push loads reaching 180 tons, shaping ground with steady force rather than speed. That power doesn't rush, it just keeps moving. Remote operation is used where mine shafts create collapse risks, keeping operators away from danger. Seeing a dozer this large respond calmly to remote input feels unreal for a second. Only around 70 exist worldwide, and Kaipara Limited operates the only 2 in New Zealand. Size here isn't for show, it's insurance. Thin stone chips locked in place can quietly extend a road's working life beyond traffic wear, and this video explains how chip sealing does that. A clean pavement surface is prepared, then a controlled spray of liquid asphalt binder is applied evenly across the lane. Aggregate chips are spread immediately, and timing here feels like a race against gravity. Rollers pass over the surface to press each stone into the binder. Excess chips are swept away after bonding. The sealed layer blocks water intrusion and limits oxidation, slowing pavement aging over time effectively. That small layer ends up doing more work than it looks like.
"500 tons is not just a number here. It's a working promise delivered by the Liebherr LTM 1500-8.1, as Gruis Martin brings this mobile crane into operation. Built for jobs where reach and strength must coexist, this machine combines flexibility with serious lifting authority. That moment when the crane rolls in fully prepared already says a lot. Assembly begins with positioning the 16x8x12 carrier, creating a stable base before any lifting configuration comes into play. The total counterweight package reaches 165 tons, added in stages to match the planned setup. Telescopic boom sections are extended from 16.1 meters toward their full 84-meter length, each section aligned to maintain balance and control. You don't rush a crane like this, it sets its own pace. With the main boom established, lattice extensions and luffing jib options are introduced depending on the working radius. The crane is capable of lifting up to 500 tons at a 3-meter radius, while longer configurations allow work out to a maximum radius of 108 meters. Underhook height can reach 142 meters, opening access to demanding vertical jobs. That height suddenly changes how the entire site feels. Power comes from Liebherr turbo diesel engines designed separately for travel and crane operation. The 8-cylinder 500-kilowatt engine handles crane functions, while the carrier relies on a 240-kilowatt turbo diesel to move the machine at speeds up to 80 kilometers per hour. Hard to ignore how smoothly all that mass moves. During transport, components are arranged for efficiency, allowing relocation without excessive disassembly. Once on site, the crane transitions back into lifting mode through a controlled sequence of setup steps. At a 20-meter radius with a luffing jib in configuration 4, it can lift 85 tons, showing how adaptable the system really is. This is the kind of setup that makes planners breathe easier. Gruas Martin's presentation highlights how the LTM 1500-8.1 operates as a universal solution, combining reach, load capacity, and mobility in a single platform. Seeing everything come together like this just feels right. Working below the waterline changes how heavy equipment is judged, and the Komatsu D155W proves that power can stay reliable even when submerged. Designed for underwater operations, this bulldozer played a key role in restoring a harbor damaged by the tsunami in Iwate Prefecture, Japan. That alone sets a different expectation before anything even moves. Deployment begins with preparing the sealed structure that allows the D155W to operate underwater. Its reinforced body, protected components, and specialized cooling system make sustained submersion possible. Once positioned, the machine transitions smoothly into underwater travel, maintaining traction and balance on uneven harbor floors. Seeing a bulldozer move like this underwater just feels unreal. Blade operations follow, focused on clearing debris and reshaping the seabed. The D155W pushes sediment, broken concrete, and scattered material away from damaged zones, rebuilding stable ground for future harbor use. Each pass reshapes the working area gradually, prioritizing control over speed. This is not brute force guessing its way forward. As work continues, operators rely on precise control systems adapted for limited visibility. Steering and blade adjustments respond steadily, allowing accurate material placement even when visual feedback is restricted. The bulldozer maintains consistent performance without abrupt movement, supporting long working hours underwater. That kind of stability changes what recovery timelines look like. Transporting material underwater requires careful coordination, and the D155W handles repeated cycles without interruption. Its ability to operate continuously beneath the surface reduces the need for auxiliary equipment, simplifying the recovery process. Less swapping machines means fewer headaches on site. Throughout the harbor restoration, the Komatsu D155W demonstrates how specialized machinery can extend traditional earth-moving into extreme environments. The rebuilt seabed restores functionality to the port, allowing further reconstruction above water. A machine like this quietly rewrites what heavy equipment is expected to handle. What happens to everyday life when an excavator demolishes the house across the street? Filmed from a living room window. Filmed by hand, the footage captures a neighboring house being taken down piece by piece, turning everyday mornings into a front-row seat for controlled destruction. The work unfolds with site preparation and positioning. The excavator rolls in, stabilizes, and begins separating outer sections from the main structure. Walls are loosened, pulled inward, and reduced in stages rather than forced all at once. This measured approach limits uncontrolled collapse while keeping debris predictable. There's a strange calm in how methodical the machine stays. Each controlled pull shows how demolition relies on sequencing rather than brute force. As demolition advances, upper sections are brought down first. Roof elements fold inward, followed by load-bearing walls that once defined rooms and corridors. Each movement resets the silhouette of the house, changing the light and space around it. Seeing rooms disappear, this quickly feels unreal, even without stepping outside. Structural priorities become visible as the machine targets connections instead of surfaces. Midway through the teardown, material sorting becomes more visible. Wood, masonry, and mixed debris are shifted into separate piles as the excavator alternates between breaking and clearing. The machine's bucket switches roles smoothly, acting as both a breaker and a mover. That bucket does more thinking than it gets credit for. This separation on-site reduces later handling and speeds up removal. With the main structure gone, attention shifts to the foundation. Concrete slabs are fractured and lifted away, flattening what used to be a lived-in space. The ground is leveled gradually, preparing the site for whatever comes next. It's wild how a home turns into a blank surface so fast. The foundation stage confirms the demolition is nearing completion. Throughout the process, the handheld filming adds a human layer. By the end, the excavator finishes clearing the last remnants, leaving an empty lot where a house once stood. From this fixed viewpoint, the entire life cycle of removal plays out without interruption. Nothing dramatic happens at the end, yet the result is absolute. Operators guide a Cartisler Machine demolition machine to dismantle buildings through controlled force rather than uncontrolled collapse. The machine positions its reinforced arm against load-bearing sections, applying force gradually so fractures travel predictably through concrete and brick. You can sense how much planning sits behind each push. Hydraulic pressure increases in short cycles, allowing the attachment to crack walls while keeping debris direction controlled. Sections fall inward rather than outward, reducing risk around the site. That inward break feels oddly reassuring for something meant to destroy. The operator repositions the machine repeatedly, targeting columns, slabs, and joints in a calculated order instead of random tearing. As larger segments loosen, the arm pulls and twists to separate material layers, exposing steel reinforcement for secondary removal. Dust rises, but movement remains deliberate. This isn't speed-driven work, it's decision-driven. Debris piles are managed between strikes to keep access paths clear for the next approach. Near ground level, force application changes again. Smaller bites prevent sudden shifts that could destabilize the machine. Seeing the structure give up its final resistance hits harder than expected. The demolition concludes with the site reduced to sortable rubble, leaving steel, concrete, and space ready for the next phase. Cartisler Machine demonstrates how controlled force, sequencing, and operator judgment define modern building demolition. During export cable pull-in for the Walney Extension offshore wind farm, the Maersk connector undergoes engineered grounding at Morecambe Bay. This operation focuses on positioning the vessel precisely on the seabed to stabilize cable handling loads before tension increases offshore. Ballast adjustments and anchor coordination work together to control trim and heading while seabed conditions are continuously verified. The grounding point is calculated to distribute weight evenly across the hull, reducing movement during cable alignment. That stability matters when hundreds of tons are quietly managed below the surface. Once contact is confirmed, winches manage controlled pull-in speed while monitoring systems track tension and seabed response. Support vessels maintain position and clearance, keeping the operation synchronized across the spread. There's a moment here where everything feels locked in, and it's hard not to lean forward. With the export cable guided safely ashore, the Mars connector completes its role in preparing the offshore link. This engineered grounding supports efficiency and risk control during one of the most demanding phases of wind farm connection. Heavy boiler units are positioned for shipping using a reinforced forklift at Sheng Chang Boiler. The forklift approaches the staging area with forks set low, aligning carefully with the boiler's base so contact points remain stable. Once engaged, hydraulic lift raises the load gradually, allowing operators to confirm center alignment before forward movement. That pause says more about control than caution. Guidance signals coordinate steering as the forklift advances toward the container entrance. Small steering corrections keep the boiler centered, while floor clearance is checked continuously. You can feel how unforgiving the margins are just by following the wheel angle. As the forks rise, mass tilt compensates for weight shift, keeping the boiler level while crossing the container threshold. Inside the container, movement slows further. Operators adjust lift height in short increments so the boiler clears the ceiling without drifting sideways. Floor rollers and guide blocks assist positioning, reducing friction during the final push. This is one of those steps where everything depends on alignment, not force. Once the boiler reaches its marked position, the forklift holds steady while securing teams lock it in place. Fork pressure is released gradually to avoid load rebound. Seeing the forks slide out cleanly feels more relieving than expected. The forklift then reverses in a straight line, maintaining mast stability until fully clear. Throughout the operation, communication stays constant to prevent sudden moves. The reinforced forklift proves its role by managing weight, reach, and stability without interruption. There's a quiet moment when the container finally looks complete. By the end, the boiler sits fixed for transport, and the forklift resets for the next cycle. This container loading sequence highlights how controlled lifting, positioning discipline, and coordinated timing keep heavy boiler handling efficient at Sheng Chang Boiler.
After decades offshore, the Statfjord Sea Loading Buoy enters its final operation as removal work unfolds in Vatsfjord. Towed for 5 days, the structure is anchored, boarded, and cleared of hazardous materials before dismantling. Heavy tugs, workboats, and ROV systems position a North Sea barge to lift the buoy by its base. That scale hits differently when 10,000 tons leave the water. Oil traces discovered during tilting halt work immediately, triggering pumps and inspections. Crews track a slow leak formed over 28 years, address it, then resume. 3 years of planning finally pay off here. The buoy reaches shore without injuries or major HSE incidents reported.
Power on the rig floor changes the moment a super single connection is lined up on this drilling rig in Canada. Instead of handling short pipe sections, the crew works with longer stands that reduce handling cycles and keep momentum steady. The derrickman positions the super single, while the top drive aligns the threads with controlled movement, keeping the connection straight under load. Hydraulic slips take weight smoothly, allowing the rotary table to stay stable as torque is applied. That clean alignment saves time you don't get back later. As torque builds, sensors monitor load to avoid thread damage while the connection tightens to spec. The system holds rotation steady, preventing sudden grabs that could stress the pipe body. Once the joint is secured, weight transfers back to the hook and the stand is lowered into the wellbore. This is where efficiency quietly stacks up connection after connection. Using a super single conventional setup cuts the number of connections compared to standard singles, reducing pauses in drilling. Fewer stops means smoother weight-on-bit control and more consistent penetration rates. The rig crew coordinates slips, elevators, and top drive timing to keep the sequence flowing. Miss the timing here, and the whole floor feels it. By repeating this cycle, the rig maintains drilling speed while limiting wear on equipment. It's one of those operations that looks simple until you realize how much can go wrong. On this Canadian drilling rig, super single connections help keep progress steady downhole. Loader coordination takes priority as 3 scoops and 5 scoops handle material flow in coal mining. Material is released from the pit wall and guided toward the loaders, which position their buckets precisely to control load balance during each pass. The 3 scoops unit handles tighter zones, focusing on selective removal, where accuracy keeps haul routes clear. Nearby, the 5 scoops machine targets bulk movement, filling its bucket in fewer cycles to reduce idle time. That contrast makes the workflow feel intentional rather than rushed. Once filled, each bucket is raised, tilted, and stabilized before the loader reverses toward waiting haul trucks. Tire grip and steering angle are adjusted constantly to match ground resistance and slope changes. Operators rely on visual markers and engine feedback to avoid overloading while keeping cycle time steady. You can almost feel the weight transfer just by following the bucket motion. Dumping is timed so trucks receive even distribution, preventing uneven axle loads that could slow transport. As trucks depart, loaders immediately reset position, keeping the pit face active without congestion. The 3 scoops loader returns to detail work along edges and seams, while the 5 scoops continues stripping larger volumes. Seeing both machines' alternate roles makes the scale click fast. Throughout the shift, coordination matters more than speed alone. Small delays compound quickly when material flow breaks, so consistency stays prioritized over aggressive pushing. There's a quiet confidence in how nothing feels forced. By the end of each cycle set, the pit profile is reshaped gradually, hull roads remain passable, and coal extraction stays continuous.